Let us take a look at another example of the recursion. This time, it's probably not going to be a good one. Starting with the problem definition, Fibonacci numbers. I don't know how many of you guys heard about Fibonacci numbers before, but if you watch the movie or read the novel of Da Vinci Code, this is actually appeared in the novel as well as in the movie. So what is a Fibonacci number? Fibonacci number is defined as starting with value of 0, then it will go to the next one, which is going to get a 1. And then the next value will be the sum of the previous two values. So you can see that the third value is the sum of the first one and the second one, which 0 plus 1 is still 1. The next value will be the previous sum, which is going to give 2. The next one will be 2 plus 1 equal to 3. The next one is 5. The next one is 8. 3 plus 5 equal to 8. The next one is 13. 5 plus 8 equal to 13. And it will be able to keep going on and on without any limitation. So the numbers will end up with pretty big when n goes big. And this is something we will be able to see quickly by writing a program. In the end of this video, we can take a look of those crazy numbers. So that's the definition of the Fibonacci number. The sum of the value will be the sum of the previous two values will be the values that we are looking at. And therefore, take a look of this mathematical definition. When n equals to 0, we get a 0. When n equals to 1, we get a 1. And that's like our base case scenario. Now, if we move on from those two base case scenario, the general case scenario would be the value that we are looking at is the sum of the previous value and the previous value. So that is how we'll be able to define the Fibonacci numbers. And therefore, if we base on the given definition, when n equal to 0, we get a value of 0. When n equals to 1, we get a value of 1. When n equals to 2, we get the sum of previous 2. When n equal to 3, we get the sum of previous 2. And this is like the table that we will be able to get. When n equals to 8, we get a value of 21. So, since we define this problem as the mathematical definition we see over here, it can be easily converted into a recursive program, because this mathematical definition basically gives us the base case and the general case. And of course, one more thing I want to mention is that although the backbone of the recursive function has the base case as well as general case scenario, there's no limitation of how many base case that you can have as well as how many general scenarios you can have. In this case, we have 2 base case scenario and 1 general case scenario. Later, we will be able to see many different kind of variations over here. So, based on the Fibonacci definitions, if we try to write a Fibonacci number recursive program, you can see that when n equal to 0, we get a value of 0. When n equals to 1, we get a value of 1. So when n is less or equal to 1, we get the value of n value. Otherwise, we simply return Fibonacci n minus 1 plus Fibonacci n minus 2. You can see that this recursive code is actually super easy to be understand. And it's almost the mirror reflection of the mathematical definition. So first of all, try to understand this is actually going to give us the right value of the Fibonacci values. The only catch is this. If we try to trace the code and try to understand it, you will actually see some problems happens over here. So let's take a look at this. Saying that if we call Fibonacci of 5, so ideally you know that Fibonacci of 5 is going to give you the value of 5, and because it's the previous values that generates the current value. So when we call Fibonacci of 5, what you will do, because it's not the base case scenario, you will hit the general case. So you will call the sum of Fibonacci 4 plus Fibonacci of 3. When the program sees Fibonacci of 4, immediately it will cause n equals to 4 and then form another recursive call. And therefore, you will call Fibonacci 3 plus Fibonacci 2. Fibonacci 3 immediately will call the n value. It will go over here. Fibonacci 2 will cause the value, and you will call Fibonacci of 1 plus Fibonacci of 0. when we see Fibonacci of 1, it will call the recursive function, and because this is the base case scenario, it will return the value of 1. So we will be able to get a value of 1 back to where it calls it. So you can see that we will get a 1 over here, and now the program need to process Fibonacci of 0. So it will create another recursive function call, n equal to 0, it will return 0, come back over here, getting the value. So we get a value of 1, so that we can return that 1 back to Fibonacci of 2. And now you need to handle Fibonacci of 1 more time. So you will see n equals to 1, you will return 1, go back over here, get a value of 2. So we will be able to get 2, go back Fibonacci of 3, which we can verify the answer. Fibonacci of 3 is indeed getting a value of 2. So when that's happening, we get a 2 over here, and you may notice we still need to call Fibonacci of 2 here. So when Fibonacci of 2 calls, it will come over here, call Fibonacci 1 plus Fibonacci 0. You can image that Fibonacci 1 will get a value of 1 by calling a recursive function call. And Fibonacci 0 need to do that one more time, hit the base case scenario, come back, get a value, and then come back over here, understanding that Fibonacci of 4 is actually the value of 3, so we can come back over here, get the value of 3, and guess what? Fibonacci 3 need to call the whole function one more time. So you may notice that there's actually a lot of redundant works that has to be done, because Fibonacci of 3 is already calculated when we were doing Fibonacci of 4. But this program does not remember those values and then keep recalculating and recalculating and recalculating. And you can see that we are only calling a Fibonacci of 5. And you need to do a lot of redundancy works already. It will cost you a lot of time as well as the resources in terms of the memory, runtime stack, those processing time and space. So it's actually not a good idea to write a recursive function call for Fibonacci values. This definition will lead to an exponential running time because there's too much of redundant work. It's not necessarily to use a recursive function. So what I want you guys to do on this video is that pause the video, get a pen and paper, try to see that how would you write a Fibonacci number code without using the recursive, in terms of simply use a loop approach. And you know what? The even better way is actually pull out your Visual Studio, write a program to see that how would you be able to write a code that using a loop to get the Fibonacci numbers. When you come back, I want to talk about there are two versions of the loop code that are going to give you the right Fibonacci number. And it's actually pretty interesting to see it. So please pause the video and then try to work on this problem. Assuming you are coming back, let's take a look of the code that I provide. So you can see that the first one is actually a very straightforward one, saying that n equal to 6, simply that's the Fibonacci number that we are interested in. And of course it can be a large number since it is computers to do the calculation. There's actually not much of limitation besides the data type that you define. So let's take a look at this. Saying n equal to 6, we need to create two base case scenarios, saying that Fibonacci 1 equal to 0, Fibonacci 2 equal to 1. So those are the two base cases that we have, and we need to define a Fibonacci value to help us calculate the next value. So you can see that after that, we're starting with a loop over here, and we basically, first of all, generate the next Fibonacci value. Fibonacci value equal to Fibonacci 1 plus Fibonacci 2, so we will get the n equals to 2 Fibonacci value, which is 1. And then we basically shift the values. So we make Fibonacci 1 equal to Fibonacci 2, Fibonacci 2 equals to Fibonacci, and then we will be able to have the new values of Fibonacci 1 and Fibonacci 2. And then we will keep looping, and then we will be able to calculate the next value and the next value and the next value. So of course, this one uses a very small amount of resource because there's only four integer variables for us to keep track of what is the next Fibonacci value is going to be. It's very efficient and a very nice piece of code. However, I like the other one better. You may have noticed that I am a big fan of array. So whatever things can use array to solve the problem, I enjoy doing that. And therefore, let's take a look at this one. This is another version that I like most. And we create a main function defining what's the whatever the n value is going to be, say 40. This is actually very surprisingly that gives you a very large amount of value. And then we simply define a large array that can hold most of possible spaces over here. And of course, I simply put 100 over here. Defining Fibonacci of 0 equals to 0, defining Fibonacci 1 equals to 1. So we have putting the first two values over there. And then what's the difference between this code and the previous code is that I don't actually need to have three variables to help me shifting all the values, swapping all the values. I use array to keep track all of the Fibonacci values. So you can see what's happening over here is that starting from the index I of 2, I simply using the previous two values sums up together, put that into my array. And now when I move to my next space of the array, they will be able to calculate the next two, the sum of next two previous two values already. So by doing so, we use array to keep track every single Fibonacci number has been generated, and that is going to help us getting the values that we are interested in. I wrote, this is the code that I wrote. So if we take a look of this code over here, I want you to notice one thing over here. When I was doing Fibonacci of the 40 and then say INTI over here, this you may feel surprised when the Fibonacci value starting with 0 and 1 sums all the things together. If we go all the way to 40, we actually end up with a very large number. Take a look of how crazy it is. It's only n equal to 40, and we get this large amount of data already, this large amount of values already. If I go 50, it's actually give us something crazy. And I want you guys to see when I change that, simply change that to 50, you actually get a negative value. So it's obviously not going to be correct. And that's why when you were seeing this code in the beginning, I make it a double, so that we would be able to have a large amount of value to store the value, so that when we runs up to 50, you see that this value is actually going to be pretty crazy. So those are the interesting things I want you guys to see, how Fibonacci value will be able to grow from a small numbers to a huge number. And of course, luckily, it is computer to calculating the values for us. And so this is actually the video that wants to talk to you about sometimes recursive function can be easily understandable. The code is almost a mirror reflection of the mathematical definition. However, it may not be a good situation for the problem. And simply a for loop plus, you can see an array is actually giving you a very easy understandable code to generate the Fibonacci numbers that we are interested in. And of course, sometimes it may not work, but sometimes it will work pretty well. The next video I want to look into is actually the tree definition. That's something I have promised you guys that we will come back and then to see how does the traversal work on the tree problems. You wrote some lab code on that one, and now it is time for you to fully understand about the recursive running on the trees.